Dimitrios Skarlatos from Carnegie Mellon University. And we're going to start now with MetaLeak, the first talk. Feng is a professor at UCF, and he's going to be presenting the work. Unfortunately, the student couldn't make it. His work is on computer architecture and microarchitecture security. So, yeah, Feng, please take it on.
Thanks for the introduction. My name is Feng Yao. I'm a professor at University of Central Florida. So today I'm going to present our paper, MetaLeak, Uncovering Side Channels in Secure Process Architectures Exploiting Metadata. This work is done with my student, Chowdhuryy, in collaboration with my colleague, Dr. Zhao. So as we have witnessed in the past few years, hardware attacks are at the forefront of computer security. Particularly, microarchitecture attacks in the form of timing channels have been demonstrated in a growing list of hardware components. Meanwhile, there are many existing attack vectors beyond digital side channels, including physical attacks. To tackle these threats, many security mechanisms are proposed or adopted individually. However, the observation we have learned from prior studies is that microarchitecture security cannot be treated as a standalone problem. As we already know, that addressing performance without considering security is a recipe for bad microarchitecture security design. In this paper, we raised the following question: how could the introduction of a security mechanism for one threat reshape the attack surface for another? So particularly, we look at one important security mechanisms called secure processor that have been studied for more than 2 decades now. Secure processor, in a nutshell, treat the processor chip as a trust boundary and offer to shield program execution from compromises by both previous software and hardware-based attacks, also known as TE these days. This is done typically through off-chip data encryption and integrity verification using processor-maintained metadata stored in memory. State-of-the-art secure processor generally maintain 3 types of metadata: counters for data encryption, MAC for data authentication, and integrity for integrity verification. And they also use metadata cache to improve performance of metadata accesses. In contrast to database exploit that has been widely studied for side channels, we want to understand whether metadata operation expose new information leakage vulnerabilities. This leads to our work, basically exploration of side channel leakage in secure process designs due to metadata maintenance. And we mainly focus on counters and integrity tree in this presentation due to limit. So we first investigate memory encryption schemes. So memory encryption is typically performed using block cipher, and counter mode encryption is mostly utilized. In a counter mode encryption, the processor maintains counters to encrypt or decrypt memory blocks. Specifically, for data read, the counter corresponding to the data block is loaded first, then used as a seed to an AES engine, which generates a one-time pad of OTP. This OTP is XORed with ciphertext to get the plain text block. Right? For data store, the counter is first incremented, and which is then go through the same process for one-time pad generation and XOR operation to encrypt data block. This is done to ensure that every write results in different ciphertext. There exist several counter mode encryption schemes in the literature, and they many differ in how counters are associated with the data blocks, including global counter, monolithic counters, and split counter. Due to time limit, I'm not discussing this in detail. So now let's look at the timing vulnerabilities in memory encryption schemes. The key observation is counters are typically subject to overflow, and upon overflow, the processor must re-encrypt data blocks that share the same counter. Right? We formulate a general abstract counter mode encryption mechanism, which is shown on the left side, and we examine it under a split counter design. As we can see, essentially, if there is a write operation to one data block, this typically involves first increment a minor counter, and then upon which we need to check whether an overflow occurs. If there's no overflow, then we can safely encrypt the current block with the incremented data, minor counter. On the other hand, as we have more writes to the data block, we have increment the counters more and more, and eventually we are close to the point of saturation. So when this minor counter is saturated, and another write comes in, it will lead to an overflow, which is detected by the underlying processor mechanism, and leads to a wraparound of the minor counter, and we have to increment now the major counter. In this case, so we have the issue a re-encryption of all the data blocks that actually share the same major counter, right? Which is actually shown in the for loop here, that we do this re-encryption for every single block in this sharing group. Essentially, what we observe as the first vulnerability class is that encryption counters actually create metadata state-dependent microarchitecture paths for writes. If you are familiar with how data accesses can be side channels, this gadget actually looks very similar to the classical scheme. A beta, we are using metadata instead of data. So essentially, we have a slower path when the program data writes leading to counter overflow, or have a faster path for regular write cases, which does not trigger overflow. And then, so next we explore the integrity verification schemes. So memory data tampering is done using integrity tree that offers strong security guarantee against replay. State-of-the-art mechanisms utilize either a hash tree that maintains where each of the load is a hash of its child loads, or a counter tree that maintains counters similar to encryption and embeds a hash along with the counters. The following figure basically shows an example of the hash tree and the counter tree. At a high level, the tree is built by gradually deriving the parent node, for example, through hashing, which eventually merges to one root. And the root is always secured on chip. As such, by verifying the hash or counters all the way up to the root, tampering can be detected. Right? Importantly, to alleviate this tree traversal cost, because it's just too much for every single read, tree loads are typically cached on chip as well. So now let's look at the timing vulnerability in integrity verification. The key observation is integrity tree traversal typically only proceed to the first cached intermediate load for performance reasons. This is because we trust the processor boundary. So similar to encryption counters, we formulate the abstract integrity verification mechanism on the left side. And let's look at an illustration of the integrity verification on the right side when we have one block B, which leads to be loaded, right? Which actually triggers an integrity verification process. So it depends on what levels of this ancestor load are cached. The verification paths can have different latencies. In this first case, we assume that the level 2 ancestor load is cached on chip. Then essentially to verify this block B, we need to first verify its direct parent node in this tree. And because it's not cached, we have to verify its parent node to verify this load itself. And eventually we lead to the cached intermediate load, which can be used for verification. So as we can see here, at the end of this verification, we have to issue 2 additional memory reads that is used to in this traversal path of the tree. And differently, in the second case, if we assume that leaf load is already cached on chip, which is trusted, then the verification path becomes much simpler, right? You just only need to verify this current block B with its direct parent. And essentially, this leads to the second class of vulnerability we identify, which is basically the integrity verification path varies according to the tree load caching status. And this is a known path where you can have multiple levels of caching possibilities. And so the integrity tree traversal can lead to data reads with highly variant latencies. So we did a latency characterization for secure process read on both simulated state-of-art architecture and Intel SGX processors. Essentially, you can look at 3 scenarios. The first scenario where the counter is cached under a bonsai local tree, which is built over counter, the tree access is not needed, which is the shortest path. And then the second scenario, which is in the middle, is when there is a counter miss, and the first level tree is a cache hit, so leading to verification from only the leaf load. And finally, on the third scenario on the right side, where multiple tree loads are missed, we perform data read operation distribution analysis, but enumerating all the possible verification paths, and the result is shown below for 2 configurations. So each cluster bar here denotes a particular verification path from no tree traversal needed to traverse all the way to the roots. So as we can see, there are highly distinguishable multi-level latencies with respect to the integrity tree accesses. And more importantly, this these latencies are not exposed in classical processors. In classical side channels, the latencies are basically hash, hit, and miss for data. So we also perform latency characterization for secure processors to write operations as we see the similar distinguishable latencies when there's overflow versus no overflow. Due to time limit, we will not discuss this in detail. So now we present two variants of MetaLeak. MetaLeak T that exploits sharing of integrity tree, and the MetaLeak C that exploits overflow of counters. So the high-level exploitation method for MetaLeak T is that since the integrity tree is actually a global structure, so the attacker can manage to locate one data block that shares a tree load at arbitrary level with a victim block, with a victim's data block, which is security sensitive. Right? In this case, now we can do something similar to a flush reload attack, but actually instead on metadata. So what it is that assume that attacker first tries to access a couple of non-relevant data accesses, which exercise the tree traversal path, load a lot of metadata of the tree to the cache, that evicts the targeted shared tree load with the victim. And then it does, the second step is we allow the victim to execute, which maybe the victim may have a secret dependent access to a data block that may exercise the tree traversal for the integrity tree metadata and bring the specific shared tree load to the cache on chip if there is access, right? Otherwise, there's no such access. And the third step is then becomes simple. So the attacker now issues a timed load of the data block that shares this tree load for verification. And the first pass means of verification actually means that the victim has access to this dependent data that make your verification metadata cached. Otherwise, it means that has not been accessed. Right? It's very similar to flush reload, but that we don't have these flush instructions for metadata. So essentially, we call this exploitation as mevict, mreload. So MetaLeak T with mevict and mreload can infer victim secret via the timing for accesses of shared tree load in integrity tree traversal. And then we have MetaLeak C, the high-level exploitation method is similar. Basically, we record that the counter overflow can lead to high latency variations. And even though encryption counter blocks may not be shared across pages, counters in the counter tree can actually have multiple levels of coverage, and it can be shared across domains. So with that, we present a technique, what we call is preset overflow. Essentially, assume that attacker and victim have a shared counter which will be incremented together. So attacker first preset the counter through a sequence write operation so that the status of this shared counter is just one write short of saturation. Right? And then we wait for the victim execution, which would have maybe a secret-dependent write operation. Right? If that write operation initiated, then the counter would be saturated fully. Otherwise, the counter will still have one more write to go. Right? And then in the third step, the attacker can infer the counter overflow, essentially the write operation from the victim, by issue another additional write and observing whether there's no latency related to overflow. And of course, write is not on the critical path of execution, so what we do is actually we issue a subsequent read operation after this write, and to time this latency for this read operation. Right? At high level, MetaLeak C allows monitoring of victims' targeted write while inferring the counter state. So we investigated both the state-of-art academic designs as well as commercial implementations using Intel SGX processors. Due to time limit, I'm not going to discuss in detail about these configurations. Please refer more to the paper. So we have a couple of case studies. Here we're going to actually present two on MetaLeak T. The first case study is in a demonstrated on a simulation environment that prototype state-of-the-art hash tree-based integrity verification. We demonstrate MetaLeak T in this infrastructure using libjpeg. So libjpeg essentially is a compression algorithm that uses Huffman coding. And in this specific slide of code, which probably is a little bit small to see, but high level, we have a array called block that essentially, and then there's a branch action based on this block value to decide to have two different branch operations. And this block is actually stores a per block entropy, which is demonstrate the changes of in image patterns across blocks of images. So these are used to later actually converted to generate a JPEG image. Essentially, by actually inferring the value of this block array, we know the entropy of this figure, and we use that to recover the original figure. But instead of actually using data flow to recover this, we're trying to use MetaLeak to observe the metadata control flow to infer this data access. So the attack setup is that we carefully choose 2 data blocks, which actually achieves a tree load sharing for integrity tree at corresponding to each of the memory access across these 2 branches. And then we use MetaLeak T to basically monitor which metadata has been loaded due to the verification process for each of this variable in this branch. With that, we basically can recover a lot of information about this block array. And this result basically shows this first shows the original image, and then we have an oracle image, assume we know exactly the block values. And the first row, last row shows a MetaLeak attack, which can show a very high fidelity of recovery of the images based on the metadata accesses. And we see that the weak access detection rate can be as high as 94%. And we did another case study on SCX processor in real hardware using MetaLeak T against libgcrypt. So libgcrypt, this is a vulnerable application where we have the scroll and a multiply algorithm that differences based on a security exponent, right? So we used MetaLeak T again to monitor whether, which specific function has been executed. Again, using metadata. And then this figure on the bottom left shows latencies for the verification pass when we have this function access versus not. And overall, we achieve accuracy of 91% for recovering the secret. So now we have shown this attack. So what's the uniqueness of this MetaLeak side channels? Well, the first thing I want to mention is that MetaLeak reveals a new dimension for microarchitecture information leakage, which is exploitation of metadata instead of data. And more importantly, we know that existing microarchitecture defenses against data access-based leakage are ineffective for metadata. For example, we have cache randomization and partitioning that are used to stop conflict-based attack. However, MetaLeak can exploit the implicit sharing of metadata, which is non-conflict based by design. And then probably existing works that actually stop sharing-based attack basically does, what they do is that they duplicate read-only as a shared data, say libraries, which is used to defeat shared memory attack. However, the security metadata in secure processors are both readable and writable memory, which means that you cannot easily just duplicate them without causing coherence issues. As a result, we mentioned that mitigation requires rethink of architecture support in secure processors. So as a conclusion, we present the first side channel leakage in secure processor designs. We demonstrate MetaLeak, a new dimension of leakage exploiting metadata. We designed a lot of attack mechanisms to create metadata-based timing channels. And we demonstrate extensive case studies on both academic and commercial designs. And there are more details in the paper, including different case studies and attack mechanisms on MetaLeak C. And please refer to the paper if you're interested. Thank you.
Great talk, Daniel. Thank you. So everyone, whenever you have questions, please go to the mic in the center, name your affiliation, and ask your questions.
Hi, thank you for the talk. Tamara Lehman from University of Colorado Boulder. So my question to you is, usually integrity trees, the higher up nodes, cover large amounts of data. So I guess I'm not too clear on how you can actually infer the secret data by sharing, like say, like even the node right above the leaves, like it's already like 32 kilobytes of data. So how can you actually infer the data at such a high granularity?
That's a very good question. So I think you're asking about the granularity in terms of data, right? So essentially, depends on the different designs of integrity tree. I mean, let's say in one design, most of the design, if you use bonsai Merkle tree over counters, then the observability is actually at the page level. So each page is one counter block, and that counter block is actually, we build the integrity tree over that counter block, right? So that's actually a page level. And so it's not as fine-grained as a, let's say, flash reload data cache attack, but what we actually want to emphasize is that this is actually in a potential temperature that cannot be easily defended by existing mitigation methods.
But I guess, like, even at a page current, like, and that's at the leaf, right? Like, when you get one level above that, it's ×8, right? So how can you actually infer data from that? I'm missing that point.
Well, that's actually solvable, right? I mean, because under the TEE threat model, the OS is malicious. The OS can actually control at what level of the tree load you want this to attack data and weakness to share, right? And then there are many additional techniques such as, let's say, stepping, controlled execution, where I can use really denies certain, accesses from the system. Overall, we see that if we go higher up, you have more possibility of sharing those, but then you have more loss because there are many other accesses that are possible, right? If you go lower down, you actually can be more fine-grained in terms of what has been covered in this region. But then you need to have a controlled relocation of these two pages to actually be close together.
Thank you.
Thanks.
Thank you. Let's thank our speaker one more time. So the next speaker is Feng. He's a fourth-year PhD student from Shanghai Jiao University, and he's currently working on architecture and operating system security. Please take some.
Thanks for the introduction. Hello, everyone. I'm Feng from Shanghai Jiao University. It is my great honor to share our work as NPU trusted execution environment on integrated NPUs. Nowadays, we are seeing the contiguous development of artificial intelligence in the device side. More and more AI applications have been deployed in the mobile phones and smart cars like AI agent, self-driving, edge LLM, and so on. To facilitate this AI computing in the device, current mobile chips have integrated an AI-specific accelerator called Neural Processing Unit, or NPU, into the SoC. Neural Processing Unit have several specific hardware structures for AI workloads. First, NPU adopts the multi-core architectures, with each NPU core contains several matrix and vector units. Second, NPU leverages a large on-chip memory called Scratchpad. Different from other memory systems, Scratchpad is managed by the software without any hardware mechanisms like memory coherence and address association. Third, to facilitate the data transfers between the multiple NPU cores, NPU utilize the inter-core interconnections mechanisms such as network on chip. However, integrating the NPU into the SoC may introduce several new attack surfaces. First, using a compromised NPU to attack the CPU side resource. NPU has a strong memory access capability, including to access the personal sensitive data stored in the CPU memory. Second, when considering the multitask scenarios, an attacker's task can leverage the inner NPU hardware structures like Scratchpad and NOC to attack the victim task running on the same NPU core. Third, CPU can utilize the vulnerability in the NPU software stack to attack the NPU tasks. The first attack is using a compromised NPU to attack the CPU side resource. The integrated NPU shares a unified memory space with the CPU, therefore it can use DMA to access any data in the CPU side cache or memory. To restrict the NPU access capability, different types of NPU may adopt different memory access control mechanisms, including IOMMU, NPU side MMU, or CPU side MMU. However, these mechanisms both use external modules with the page-level isolations, which is complex and inefficient. We propose a more efficient memory access control mechanism which fully utilizes the NPU allocation and access pattern. Current NPU driver will serve a contiguous memory space as NPU memory and allocate all data required by NPU in this space. During the NPU execution, it only requires 3 types of data. the input data, model weight, and output result. NPU uses DMA to load and store this data from the main memory to the on-chip SRAM. To translate the NPU's virtual address for the DMA operations, we only introduce 3 translation registers for input, weight, and output. Each translation register records the virtual address, the corresponding physical address, and the range size. Besides, we also add a new tracking registers to perform the permission check in a cross-granularity, as all NPU memory is located in a dedicated memory space. Next, I will introduce attacks from the inner NPU hardware structures like Scratchpad or NOC. After we submit our papers, a new vulnerability called leftover locals has been exploited. It can steal the model weight from the on-chip SRAM and affect a large range of NPU devices, including Apple's, AMD, and Qualcomm. The mechanism of this attack is very simple, just because there is no isolations for on-chip SRAM or Scratchpad. Therefore, a listener process can flush the data from the SRAM to the main memory and thus steal the secret. There are several strongman solutions like temporal sharing the SRAM resource. However, it needs to load and store all data in the SRAM during the task scheduling with a large NPU context. Moreover, temporal sharing is not suitable for global SRAM. Both of these limitations will introduce a large performance overhead. Another strongman solution is spatial sharing with the static partition. However, static partition has been proved to be inefficient due to the low resource utilizations, as different models require different size of SRAM. Our solution is using ID-based isolations, which is more fine-grained and dynamic. We add an ID tag for both Scratchpad entries and NPU calls. Only the NPU that has the same ID tag can read or write the data in the Scratchpad entries. Additionally, as for the local Scratchpad, NPU call can forcibly reset the ID tag of Scratchpad entries for write request if the ID tag is not matched. The second attack for the inner NPU hardware structure is leveraging the OOC network. Network on chip allows the direct data transfers between 2 NPU cores. The source node can define the directions of NOC package, and it will be transferred to the next node for each clock. Compared with the GPU architecture, NPU with the NOC can significantly reduce the memory load and store requests. To deploy the ML workload to the NPU, we need to map the computing graph to the multiple NPU cores. We separate the NPU cores into the multiple pipeline stages. Each pipeline stage is responsible for 1 layer in the computing graph. However, attackers may breach the root integrity of NPU tasks using the NOC network. Root integrity means the data flow in the NOC must be equal to that in the computing graph. There are two cases of NOC-based attacks. First, if the NPU task requires 1 times 4 NOC topology, but is given 2 times 2 NOC topologies. In this case, this NPU task may communicate with 2 NPU cores, which are controlled by the attacker. Second, attackers can inject malicious data to the victim NPU core using the NOC network. To guarantee the root integrity, we introduce the online ID authentications and offline root integrity checks. During the runtime, we use a PIP hole mechanism to isolate NOC network between the secure NPU core and the non-secure NPU core. Each NOC package is associated with an ID tag and is verified with the ID status in the target NPU core. As for the secure ML task, we also need to check whether the runtime data flow graph is matched with the expected computing graph. The third type of attacks comes from the NPU software stacks running in the CPU side. NPU has a large software stacks including the AI framework, user mode driver, and kernel mode drivers. This software stack will introduce large TCP. We propose a tiny and trusted NPU software modules called NPU Monitor. It decouples the security from the functionality for the original NPU software stack with 4 components. First is the context status, determines the hardware sources that NPU can access. Code verifiers checks the measurement of NPU code and decrypts the secure models. Trusted allocators can securely allocate the NPU's memory and the scratchpad entries. Finally, a secure loader tracks the root integrity before executing the secure NPU task. We have implemented a prototype of sNPU in our FPGA platform with RISC-V CPU core and a Gemini NPU, which has similar architecture as the Google TPU. We compare the sNPU with other NPU systems like normal NPU without any protections and Chazone NPU, which leverages the LMU to restrict the NPU memory access. First, we evaluate the performance of NPU memory access control. Using the translation registers introduce nearly zero overhead for address translations, while LMU introduces 10% overhead even with enough LTLB entries. This is because the translation burst phenomenon for NPU memory access. Second, we demonstrate how ID-based scratchpad isolation can well fit different ML models. We run 2 ML workloads concurrently within 3 groups. ID-based scratchpad isolations can dynamically adjust the scratchpad size according to different workloads. However, the static partition cannot accommodate all workloads. For example, HEAP partition is good for the mobile net with AlexNet, but it's terrible for the BERT with GoogleNet. We also evaluate the performance of NOC isolations using the PIP-hole mechanism introduced in our papers and software NOC, which leverages the memory load and store to emulate the NOC behaviors. The software NOC will introduce 2 times overhead in micro-benchmark and average 20% overhead in ML workload. However, PIP-hole mechanism will not introduce any overhead compared with the original NOC mechanisms. Now let's conclude our work. In this paper, we systematically analyze the secure hardware architectures for integrated NPUs. We define 3 attack surfaces for integrated NPUs, and we also the first work considers the isolations for inner NPU hardware structures. Besides, we also figure out that a secure ML task should guarantee its root integrity besides the code integrity. sNPU mitigates the cost of security checks from up to 20% to 0 with only incurring less than 1% hardware cost. Thank you for your listening.
Thank you. Any questions for our speaker? To get started, so you mentioned that there is some overhead on the IMMU side.
Yes.
And that the burst behavior of the applications is something that is causing the overhead. So in the IMMU case, like you mentioned that there is some overhead, right, at 10%, and there is a burst case. So can you explain a little bit more? Like, for example, are you using huge pages for IOTLB, or like is it 4 kilobyte pages? Like, what does the burst mean?
Yes. Even if we use the huge page, there is still some overhead related to LMU. This is because the translation burst phenomenon, which means in the NPU task, it will trigger DMA operations for 1 cycle, and if there is a TLB miss, it will traverse the IO page tables, and it will cause a large latency. For example, it may cause 100 cycles, and this latency cannot be reduced by adding more LTLB entries in the NPU cores. So this overhead cannot be reduced. Cannot be reduced in LMU-based isolations. And other papers have also proved this point.
What about larger entries?
Larger entries.
Larger.
Yes, our design is using the range translations, which can provide large range translations. Yes, I think in the NPU, for the NPU task, the range translation is more suitable for the page translations because the page translation has a fixed page size. Yes.
Thank you. Let's take our speaker one more time. Okay, so our next talk is going to be recorded, but we have the speaker on Zoom for questions. Wang is a 60-year PhD student in Virginia Tech. He's working on hardware security, especially secure memory systems. And he's actually going to be on the job market looking for academic positions, so please reach out to him if you want to talk more. So let's start with the video.
Morning, everyone. I'm Xiong, a PhD student at Virginia Tech. In this talk, I will present our work on addressing the performance overhead for memory encryption. Moving computing in the cloud can lower costs for many companies, but cloud computing raises new security concerns as companies no longer control physical access to the servers running their applications, especially the memory bus. For example, disgruntled cloud employees could probe the data transferred on memory bus through physical access to the server machines. This motivates the need for memory confidentiality, meaning hiding memory values from attackers. CPU encrypts DRAM blocks for confidentiality. Mainstream memory encryption today is moving from counter-mod encryption, like Intel SGS1, to encryption without counters, like Intel TME, SGS2, and AMD SEV. We call them counterless. Counter-mod encrypts each block with an increasing counter. Memory controller performs self-calculation like AES on the block's counter and XOR the result with plain text to get the ciphertext. Counter-mods protect counters with an integrity tree to securely detect physical replay. The physical replay can revert memory blocks to older values via physical access to memory. CPU cache counters and integrity tree nodes to minimize DRAM bandwidth overhead. But irregular workloads suffer from high miss rate in the counter cache, incurring significant DRAM bandwidth overhead. So memory encryption today eliminates counters. The AES calculation of counterless directly takes the data as input without counters. Different from counter-mod, counterless does not detect physical replay. It only provides encryption and detects other attacks on data integrity. Although counterless avoids bandwidth overhead, it has latency overhead. Upon the decryption for last level cache rate miss, the time-consuming self-calculation needs data as input, so the calculation can only start after the data block arrives. This increases the large cache miss latency by the latency of self-calculation compared to no encryption. For example, AES 128 takes around 10 nanoseconds according to Pliable. CPU prefetching can mitigate this AES latency overhead for regular workloads, but cannot mitigate it for irregular workloads. We evaluate the performance of irregular workloads on the counterless encryption in an Intel Silver CPU with TME. With TME turned down, the average performance drops by 9% normalized to without encryption. To address the AES latency problem of counterless, we observe that despite memory bandwidth overhead, counter-mod can calculate the cipher faster than counterless. One way for counter-mod to calculate cipher faster is through counter-cache hit. Along with DRAM access of data, memory controller also accesses the data's counter in each counter cache. Upon cache hit, memory controller uses the cache counter to calculate AES. When both AES results and the data block are ready, memory controller XOR them to get the plain text. The counter cache access is quick, so AES is in parallel with DRAM access of data, hiding the AES latency. Even for cache miss, after the counter arrives from DRAM, memory controller can use the counter value to quickly get a normalized AES result for the counter, and then XOR the AES with the data to get the plain text. For example, my prior work MCC uses a 128 entry table with hit rate more than 90% on average for irregular workloads. Also, the access in the small table takes just around 1 nanosecond, much faster than AES calculation. Based on this observation, our high-level idea is to combine the efficient memory accesses of counterless and faster self-calculation of counter-mod to achieve the best of both worlds. We name our idea as counter-led memory encryption. Counter-led combines the two encryption modes by relaxing the memory accesses of counter-mod to just meet the security requirements of counterless. As I said earlier, counterless encryption relaxes security requirements compared to counter-mod. It forgoes detection against the physical replay. Since counter-mod encryption securely detects the physical replay through the integrity tree, counter-led forgoes all accesses to the integrity tree while reading data from memory. When reading a data block, memory controller only fetches the block's counter. This initial design significantly reduces the bandwidth overhead by cutting multiple overhead accesses to single counter access. The challenge is that under a last catch miss, counter can arrive later than the data from DRAM, but the memory controller needs the counter to start the decryption. We simulated the counter model for irregular workloads and only model one overhead access, the single counter access for each last catch miss. We find that counter access alone slows down workloads by 7% on average. To address the challenge that counter arrives later than data, since the counter is small, usually less than 8 bytes, the naive idea is making the data block bigger, so we can embed the counter into the block. Then just one access to data block can bring both the data and its counter at the same time without latency overhead. But making the data block bigger calls for modifying more memory modules, which is costly. So instead of making the block bigger, CounterLite actually encodes the counter into the data block's error correction code, or ECC. We keep the data block in the standard size of a DDR5 block. A memory block in DDR5 server memory has 64 bytes for data and 16 bytes for data's ECC, in total 80 bytes. These 80 bytes are strapped across 10 different chips, with 8 bytes in each chip. 8 bytes of ECC are for error detection, another 8 bytes are for error correction. For example, prior work on secure memory, Synergy uses 8-byte message authentication code, or MAC, for error detection and 8-byte parity for correction. The MAC takes the data and its counter as input. Hardware error can cause the DRAM chip to lose its data, so memory controller uses the MAC to detect the hardware error. The 8-byte parity is the XOR result across 8 8-byte data and the 8-byte MAC. Upon an error, the CPU can use the parity to mathematically retrieve the missing data. CounterLite encryption generalizes the error correction bits of the data block to retrieve other types of information like the block's counter. CounterLite adds the data block's counter into the calculation of the block's correction bits. For example, CounterLite XORs the data block's counter for parity calculation. Under last catch miss, memory controller fetches the data block without the counter in it. Under the common case, all the data MAC and parity are correct, so memory controller can retrieve the block's counter simply through XORing data, MAC, and parity in the data block. Since no error happens, the MAC check will pass. Finally, memory controller uses the retrieved counter to quickly finish counter model decryption and verification. For example, memory controller can use the counter to access its AES results in the memorization table on the MCC. CounterLite still ensures correction on hardware errors. Let's say memory controller fetched the data block with error in the 8-byte D1. Because the corrupted D1 is the XOR input for retrieving the counter, the retrieved counter is also wrong. Then the wrong counter fails on the MAC check of the block. In this case, memory controller directly gets the correct counter by fetching the counter block in DRAM. Memory controller then recovers the D1 by XORing the correct counter, parity, MAC, and D2 to D8. The last level catch read back on the CounterLite has overhead accesses. Memory controller needs to increment the counter using the new counter value to re-encrypt the data before writing it to DRAM. Different from memory read, CounterLite still needs to update counter blocks and the integrity tree during memory write for reliability and security. We'll have more discussions about this in the paper. Updating the counter block and the integrity tree and later writing them back to DRAM incurs DRAM bandwidth overhead. In general, the overhead accesses are most harmful for performance when there's little memory bandwidth to spare. To mitigate the bandwidth overhead of last level catch write back, if the spare bandwidth is little, which is bandwidth utilization exceeds the threshold like 60% in our evaluation, counterlet adaptively switch the data block's encryption mode back to counterless while writing the data block to DRAM. We combine the performance of counterlet against the counterless and the memory systems without encryption. We simulated the memory using DDR5 bandwidth in Gen5 and model 10 nanoseconds AES latency to match with our real system measurements. Same as RMCC, we model 128 entries in the memorization table. This figure shows the last catch miss latency of counterless and counterlet. Counterlet decreases the miss latency by 7 nanoseconds compared to counterless. We also evaluate the performance of counterless and counterlet. Counterless only provides 90% of performance of no encryption. Counterlet improved the performance from 90% to 98% on average. Most benchmarks achieve speed up of more than 7.5%. For some benchmarks, like OMTP, the performance improvement is less because their heavy bandwidth overhead during write-back harms the performance. To explore how counterlet works when there's little DRAM bandwidth to spare, we also perform the stress test for DRAM with bandwidth of DDR2, so that there's little bandwidth to spare for most benchmarks. The performance degradation of counterlet encryption in the worst case, actually for the benchmark OMTP is just 1.4% of counterless. As a summary of our work, we explore and address the performance overhead of counterless. We propose counterlet to combine counterless and countermod. Counterlet encodes the counter into ECC and retrieve it from the data block for last catch misses. This significantly reduces latency and bandwidth overhead during memory rates. Counterlet improves performance by 9% compared to counterless. Thank you for your attention. I will be glad to hear from you if you would like to discuss potential collaborations or job opportunities. I'm happy to answer any questions about this talk.
Any questions for our speaker? So to get started, Zheng, you presented a memoization feature. Can you explain a little bit more how it works and if there are any security implications with the scheme?
Okay, for the memoization, because we noticed that a lot of memory blocks for the same workloads, they can share the same count value. So our idea is to memoize AES result for limited number of counter values AES results. So later, during decryption or verification, the memory block can reuse it without recalculating the AES results for decryption.
Thanks for the great talk, Alex Douglas from Georgia Tech. I think there is something I missed. So you encode additional information in the existing ECC bits. So I wonder, what is it that you're giving up by piggybacking additional information in these limited bits? Do you reduce the number of errors you can identify, or do you trade off something? Yeah.
Actually, we don't reduce the number of bits to protect actually. So we're not storing explicitly the counter into the data block. We're encoding it. So that means it doesn't occupy any bits, but it can be decoded from the existing data MAC and parity. So it's just a calculation. It's not like storing there. So our prior work is just calculate parity using the data and MAC, but the difference here, we're just calculating parity by XORing one more counter. So that's the difference.
Let's thank the speaker one more time.
Thanks.
Coming up next is Perspective, and Tay and David are going to be presenting. Both of them are undergrads at CMU, and they work with me. So, Tay, David.
this way.
Good morning. My name is David. This is my research partner, Tay. We're with Carnegie Mellon University's Computer Architecture and Operating Systems Group. Today we're presenting Perspective, a principal framework for pliable and secure speculation in the operating system. So a quick recap on what Spectre v1 is. So let's say we have a speculative execution gadget and some malicious adversary. This adversary is going to give some input X that's then going to be mispredicted on this branch, and then the following transient executions will follow. First, we'll have an arbitrary out-of-bounds read that will get some secret somewhere in memory. This secret is then transmitted through some cache side channel so that the attacker is able to learn something about this secret. So what happens if you have such a gadget in the kernel instead? Well, we have an attacker process and a victim process. In this case, the attacker process is going to make a malicious input through a syscall, in this case in the function A. And because of this, we're going to speculatively reach some gadget in the kernel. This gadget is then able to leak any memory inside the kernel, including the victim's data. Now, through another side channel, we're able to learn something about this victim's secrets. For Spectre v2, it's similar, but there's even more options for gadgets, because instead of speculative execution going through the normal chain of execution, where we would reach function B, this is actually speculatively hijacked. Instead, we reach a gadget somewhere else in the kernel, and we're once again able to leak the victim's data. So you can think of an operating system kind of like a giant room. Let's, for this case, just talk about the Linux kernel for simplicity. But you have things like the scheduler, memory management, storage, network devices, and device drivers, and even you have your fun toys like eBPF, KVM, and whatnot. And while this all sounds, all fun, it's actually a lot more bleak than it seems. Speculative execution has been plaguing the Linux kernel for quite some time, with things like mismanaged gadgets, mitigations being re-added, and even some cases of third-party devices causing speculative execution vulnerabilities as well. And because of this, we're not really sure what parts of the kernel are actually secure from these speculative execution attacks. And with Spectre v2, with control flow hijacking, it's even more possible that there are much more possibilities for attacks to happen in the future. So let's look at existing defenses. Right now, there are two types of existing defenses. First, that actually go after the speculative access. This is things like SLH or InvisiSpec. And in other cases, they go after the speculative transmission of data. This would be like STT. And these defenses are, code agnostic, which usually is very good for your architects. But in this case, this leads to either having complex hardware to implement these fixes or requiring a large overhead due to overprotection. So in this work, we present Perspective, an OS hardware interface for secure speculation in the operating system. First, we're going to introduce a unique taxonomy that talks about active and passive attacks regarding speculative execution attacks in the kernel. We're also going to talk about the Perspective OS hardware interface, introducing data speculation views, or DSVs, which talk about how data can be speculated on, and instruction speculation views, or ISVs, which talks about how instructions can be speculated on. Notably, both of these views can be associated with a given execution context, such as a process. And we're also going to introduce the Perspective design, which involves a kernel component and as well as a hardware component that can be added on top of existing hardware defenses. The kernel or software side at runtime will actually decide how DSVs and ISVs are enforced and allow us to enable simple hardware defenses on top of the existing hardware defenses that currently exist, such that we can reduce overprotection. Finally, Perspective's tailored protection with this simple hardware allows for a low overhead, about 1.2% on data center applications. And finally, we do a security analysis on how effective Perspective actually is. So let's talk about our taxonomy. The first type we have are active attacks. Active attacks, the attacker process is the one driving speculative execution. In this case, you have a malicious process that makes some syscall that accesses a gadget that's able to leak a victim's information. For a passive attack, it's the victim that's driving execution. Instead, we have hijacking again, where the victim makes a syscall, You think it's going to go one place in the kernel, but speculatively is hijacked to a gadget instead, and now the attacker is able to learn information from that leakage. And it's important to note that this taxonomy is completely agnostic to previous terms for attacks, such as Spectre v1, Ret Bleed, etc.
Based on our taxonomy, we will demonstrate how we can defend against each type of attack. Let's begin with active attacks. The fundamental issue with active attacks is that attackers can speculatively access data that do not belong to them, whether it's data owned by another victim process or data owned by the kernel. Our goal is to have the kernel communicate to the hardware the notion of data ownership. Thus, we introduce data speculation views, or DSVs, which are defined as the set of data that a given execution context owns. Then, the hardware simply blocks all speculative accesses that are outside the DSV of the current execution context. As a result, DSVs completely mitigate active transient execution attacks. DSVs provide a robust security guarantee, but how do we define such data ownership? There are many design choices possible, but we propose one approach based on allocation. We modify the operating system to track memory allocations and associate them with their corresponding execution context. Consider an explicit allocation where resources are explicitly requested by user space, for example, through mmap. Then the kernel internally calls alloc pages, and it will allocate a page represented here as a black box. Since the victim requested the page, we consider the victim owning the data. Hence, our modified kernel associates the allocated page to the victim's DSV. For implementation, tracking ownership could be implemented on Intel's TDX. Please refer to the paper for more details here. Now let's revisit our taxonomy. With active attacks mitigated through DSVs, we now turn to passive attacks. Recall that in a passive attack, the victim process executes kernel code, but the attacker process speculatively hijacks the control flow to a function of their choice. This function contains a gadget that can access and transmit the victim's data. Since the victim accesses its own data, DSVs cannot mitigate these types of attacks. The challenge here is that the attacker has a large attack surface of kernel functions to choose from. Many functions of the kernel are infrequently used, and some gadgets may be buried within those kernel functions. The goal here is to limit speculative execution of system calls to a small set of trusted kernel functions. Thus, we introduce instruction speculation views, or ISVs, which are defined as the set of kernel functions that a given execution context can speculatively execute. Then, the hardware simply blocks any speculative execution outside of this set. It's important to note that ISVs can be conservative in including functions. Excluding a function from an ISV allows it to still execute non-speculatively. Thus, we can have some performance trade-off for increased security. But how do we generate this set of functions in the first place, when the Linux kernel has millions of lines of code? For simplicity, the following example will only include the kernel code. Now consider a hypothetical situation where the victim process executes a getPID system call. GetPID directly calls other functions, which we denote with a solid line. These functions may also make indirect calls, which we show with the dotted line. Besides the functions used by getPID, the kernel includes many other functions. However, some functions, for example in the device driver, may contain an undiscovered gadget that can leak information. Now let's assume that the victim non-speculatively executes only the functions getPID, A, and C for the getPID system call. In order to restrict to such a set of kernel functions, we propose two approaches, static and dynamic. First is static. We generate a call graph of getPID and only include the direct call edges as our ISV. This is then extended to every system call the application might possibly execute. We do not track indirect call edges in our static analysis because that will lead to the entire kernel being legal targets, thus making ISVs useless. One drawback of not including indirect edges is that some frequently used functions that are only reachable by an indirect edge may not be included in the ISV, which could result in a performance overhead. An alternative approach is dynamic. We dynamically trace actively used system calls and kernel function paths using kernel-level process tracing, such as the Linux ftrace. This can capture indirect call edges that were not possible in static ISVs. Now, what practical benefits do ISVs provide? First, it reduces the attack surface by excluding unused or infrequently used kernel functions. The victim can no longer be tricked into speculatively executing irrelevant functions outside its ISV. So for example, speculative execution from function C to function D would be blocked. Second, it accelerates gadget finding by focusing on a smaller set of functions. Without the ISVs, we have to look for specter gadgets in the entire kernel. Due to path explosion, this is often intractable or too slow for tools that are based on symbolic execution, fuzzing, or taint tracking. However, with a smaller set of functions, we only need to find gadgets within the ISV. Third, we can leverage the results of gadget finding to exclude those gadgets from the ISVs. Suppose we found a gadget in function C. Then we exclude that function from the ISV to generate an enhanced ISV, or what we call ISV++. Furthermore, Perspective's OS hardware interface allows ISVs to be quickly generated or modified offline without any kernel modifications. For the performance evaluation, we model the Perspective hardware modifications on top of the Gen 5 simulator, along with our modified Linux kernel. We use LEbench as micro-benchmarks to extensively test the core operations of the operating system. We also evaluate data center applications, HTTPD, Nginx, Redis, Memcached as macro benchmarks to measure the overhead of real-world applications. Finally, we compare 4 different defense schemes. First is Fence, which is a hardware-only defense that delays speculative loads until all prior branches are resolved. Second is Perspective Static, which uses the static ISV. Third is Perspective, which uses the dynamic ISV. And last, Perspective++, which uses the enhanced ISV, the ISV++. On LEbench, we can see that all 3 versions of Perspective demonstrate a significantly lower overhead of about 3.5% compared to Fence, which has a 47.5% overhead. Data center applications also demonstrate a similar profile where Perspective has a lower overhead of 1.2% compared to 5.7% overhead of Fence.
Finally, to evaluate the effectiveness of ISVs, we modified Casper, a known fuzzer to find speculative execution gadgets in the kernel, to specifically only look inside the ISVs themselves. Here we can see that modifying Casper to only look in the ISVs is able to dramatically speed up search for relevant gadgets as much as 2 times faster. We also look at gadget reduction. In this case, we have ISV static, or static analysis, getting a fair 84%. ISV, which is just our dynamic scanning, which gets to 92%. With ISV++, we're able to constantly modify the ISV and search for known gadgets inside of it. We get a 100% reduction in gadgets. So there's more we could have talked about, but we don't have enough time. We conducted further security evaluations regarding speculative execution and how Perspective combats it. We also talk about hardware structure evaluations, the secure kernel memory slab allocator we made to help implement DSVs, as well as ISV hardware-related changes and the virtual address space related to them. So, the main takeaways. We introduce a new taxonomy for transient execution attacks, for active and passive. Based on this taxonomy, we introduce Perspective, which is an OS hardware interface that enables tailored defenses with DSVs and ISVs. And finally, for security guarantees, DSVs are completely able to combat active attacks, and ISVs reduce the attack surface of passive attacks, accelerate gadget finding for notable changes, and can swiftly mitigate new gadgets offline. Last, Perspective exhibits a minimal overhead, and compared to other things, only has simple hardware added to it, with only a 3.5% on LEbench and 1.2% on data center applications. Thank you.
Jian from MIT, great talk. I really like the part that this work reduces the attack surface so large, like the big reduction of the gadgets. I have one particular question because the appealing aspect of this is that compared to many other pure hardware-only solutions, this one seems to be much simpler. But I have one question that, how do you store this ISV, like control flow graph shape of structures in hardware? Do you need to store some things in the hardware so that the hardware can be able to track these perspectives properly? And likely, hopefully, this piece of hardware is very simple so that you do get a appealing feature compared to hardware-only solutions.
So yes, we do have part of our hardware modification is for the support of ISVs, and we talk a little bit more in depth in the paper. But to make it simpler, we do have effectively an ISV cache related to the management of ISVs, and part of the reason why we do that is so that we're able to, rather than having to recompile the whole kernel to like change an ISV, we're able to quickly substitute a change in for quick modification if like a new gadget is discovered.
Is the format of the ISV data structures like a control flow graph with a map or a list? Just a little bit more information can help me to visualize how that structure looks like.
So in the ISV, we have a list of functions that have the start and end address of each function, and the hardware simply checks whether an instruction belongs within any of the offsets of the functions.
I see. So it is a lot of pairs. That's why you need the cache.
Yeah.
Cool.
Yes.
Thanks.
Thanks, great talk. Alex Deglis from Georgia Tech. Just a quick question on the performance to get a sense of why these huge slowdowns when you use fence. So my understanding with fence is that you put fences in every time you have a speculative branch only in kernel code though, right? So this means that your end-to-end application slowdown is 50% if the only thing you do is have fences in the kernel.
Technically, this is talking about the speed in the kernel itself, not for.
So that's only time spent in the kernel. So the time that you spend in the kernel is bloated by 50%.
No, the average end-to-end latency is 50% for the LE bench micro benchmark. It is only testing like certain operations, and Fence has about a 300% overhead for system calls like epoll, poll, which constantly pull the application, and Fence can have, there's a fence every single time for each operation, and that's why there's a significant overhead, and 50% is just the average, which could be a bit skewed because of those 300% overhead by other system calls.
So that 50% is for the micro benchmarks or for all of the benchmarks you have, including the server workloads?
That's just for the micro benchmark. Okay. For the workloads, for the data center applications, the Fence has about 6% overhead, and we have 1.5%.
Let's thank our speakers one more time. Okay, next talk is HEAP. We're going to talk about fully homomorphic encryption, following up on today's keynote. Razmi Agrawal is going to present. She's a research scientist at Boston University and a visiting scientist at MIT. Her research interests include crypto, hardware, and post-quantum cryptography, also with FHE in the mix. With that, Razmi, please take it away.
Yeah, so thanks for the introduction and good morning all. So I'm going to present our work HEAP, a fully homomorphic encryption accelerator with parallelized bootstrapping. So this work was funded through Red Hat Collaboratory at Boston University. So as we know, data breaches are on the rise. There were more than 3,000 data breaches in 2023, compromising more than 8 billion data records. And the average cost of a data breach worldwide also continues to rise steadily, reaching $4.45 million just in 2023. And even though various data security and privacy measures are in place in the cloud, about half of the total data breaches were cloud-based. So can we do anything different to protect the data in the cloud? I would say yes, for sure. We can use fully homomorphic encryption, or FHE for short, which enables computing on encrypted data, thus protecting the data owner's private data while it is shared with the untrusted third-party cloud servers for processing. So with server having no access to the data owner's secret key, the server cannot learn anything about the data, and even if a data breach happens, the malicious actors cannot access the data. So there are many FHE schemes out there, but the FHE scheme that is of interest to us is the CKKS scheme, as it allows operations on real numbers and thus can naturally support real-world machine learning applications. So this is great, right? FHE provides a strong data security and privacy guarantees, and CKKS scheme enables real-world machine learning applications. However, the issue is that the noise that was added during data encryption for security purposes becomes difficult to manage. So as we perform various homomorphic operations, the underlying noise begins to grow. For example, add doubles the noise and multiplication squares it. So to prevent the underlying data from getting corrupted by this noise growth, we need to use either large parameters so that there is enough room to perform all operations within the application, or we need to perform an expensive operation known as bootstrapping. Bootstrapping operation denoises the ciphertext by homomorphically evaluating the decryption circuit. So realistically, no designer or architect wants to deal with several thousand bit operands. So going just for the large parameter set solution is not an option. Typical choice is to select a manageable parameter set along with bootstrapping. However, it turns out that the bootstrapping operation itself is quite slow. So first CKK's bootstrapping implementation on a CPU took about 8 minutes. With all the algorithmic and hardware design improvements over the past 3-4 years, one of the GPU implementations reduced this bootstrapping time by 350 times, and subsequent FPGA and ASIC implementations reduced it further, bringing it down to almost 0.4 milliseconds. So even when the performance improvement in bootstrapping is quite impressive, it is observed that when performing an end-to-end machine learning application evaluation, up to 95% of the time can be spent in bootstrapping. Moreover, one of the recent FPGA implementations tried scaling the logistic regression model training to multiple FPGAs and observed only 20% performance improvement, for the reason being that the performance was limited by bootstrapping, as it was challenging to parallelize bootstrapping on multiple FPGAs. Hence, there is a need to further optimize the bootstrapping performance, but for that, we first need to understand why bootstrapping is slow. So the reason why bootstrapping is super slow is that, first, bootstrapping itself consumes up to 16 to 17 limbs of the ciphertext, implying to work with at least n equal to 2 to the power 16 or 17 parameter set to have enough limbs to perform bootstrapping, and then the operations in the application under evaluation. If one were to go with a smaller parameter set, like n equal to 2 to the power 13, there won't be enough limbs in the ciphertext to perform even bootstrapping. So with these large parameters and smaller caches, a lot of time goes in shuttling the data between the on-chip memory and the main memory. And second, the bootstrapping operation comprises of HEAP and rotate operations, which requires performing key switch operations. And if we look at the sub-operations in the key switch operation, some operations are limb-wise and some are slot-wise. Limb-wise operations can be done independently on the limbs of the ciphertext and are thus easy to parallelize. But slot-wise operations require interaction between the slots of the limbs and are hard to parallelize. So if different limbs are scheduled on different compute devices, the communication between these devices will be very high to meet these data dependencies. So we address these two challenges in this work by introducing a hybrid scheme switching approach, wherein we perform operations within the application using CKK's primitive operations, but however, when it comes to performing bootstrapping, we switch to TFHE and utilize the programmability feature of the TFHE scheme. So in this example here on the slide that performs logistic regression model training, the iterations within the logistic regression model training are performed using CKKS operations, while bootstrapping after every iteration is performed using TFHE operation. So now, how does the bootstrapping work, and what are the advantages of this approach? So to answer this, let's look at the typical CKKS bootstrapping steps first. So CKKS bootstrapping works by taking a ring learning with error or RLWE ciphertext as an input, converts it from coefficient to slot representation, then performs modular reduction homomorphically to get rid of the additional KQ term, and then converts the ciphertext back to coefficient representation, and the output is an RLWE ciphertext. So now in the hybrid approach, we perform sample extraction on the input RLWE ciphertext to generate small n LWE ciphertext. So as a reminder, small n is the number of slots that are actually used in the ciphertext, and for a fully packed ciphertext, it is equal to capital N by 2. Now we can distribute these small n by number of compute units, LWE ciphertext, to each of the compute unit and perform operations on them in parallel. The modular reduction operation is embedded within the blind rotate operation as lookup table operations. The blind rotate operation generates n ring learning with error ciphertext with only one slot having the useful information. So then we again have to perform the sample extraction operation and get n LWE ciphertexts, which are repacked to obtain a single RLWE ciphertext. So with this approach, we can use n equal to 2 to the power 13 parameter set, as now the bootstrapping consumes only a single lim of the ciphertext while performing a rescale operation after the repacking. And one of the main advantages is that this hybrid scheme switching approach reduces the key reads from main memory by about 18x. So we did a proof of concept implementation of this proposed hybrid scheme switching approach in the form of HEAP. So HEAP itself is a single FPGA 36-bit design, and the microarchitecture of HEAP consists of 512 functional units, register files, on-chip memory, and various control units. And the FPGA that we used here is AMD U280 Accelerator card. Then for the overall system design, the single FPGA implementation is ported to 8 FPGAs, along with the read-write 5-4 HBM, and the interaction between the FPGAs happening using a 100 gig Ethernet switch. And on top of this, there are a lot of optimizations that are implemented. For example, optimizations at the microarchitecture level, then data path optimizations to the entity, and the blind rotate operation, and many more. Please refer to the paper for details. In terms of the performance evaluation, we first compare the performance of a fully packed bootstrapping operation. So we compare the amortized multiplication time per slot to make a fair comparison with all the other existing implementations. This is important because different implementations use different parameters, and this equation takes into account these differences. So as we can see on the plot here, HEAP outperforms all existing CPU, GPU, FPGA, and ASIC implementations. In fact, if we were to compare the performance in terms of clock cycles, then HEAP outperforms ARC ASIC design and gives almost same performance as Sharp ASIC design. The difference in operating frequency makes HEAP a bit slower when comparing the absolute times. We also evaluated a couple of applications to see how HEAP performs. One thing to note here is that the bootstrapping is not fully packed. So for logistic regression model training, only 256 slots in the ciphertext are packed, while for ResNet 20 inference, 1024 slots are packed, which means that there are only 256 or 1024 LWE ciphertexts to process in parallel, which further improves the performance of HEAP. So for logistic regression model training, one other important comparison is between Fab2, which is also an 8 FPGA implementation, as HEAP. And we can see now the performance improvement is huge with parallelized bootstrapping implementation in HEAP. So to summarize, we parallelized the CKKS bootstrapping using a hybrid scheme switching approach. We also propose a novel multi-compute platform FHE accelerator called HEAP, which supports parallelized CKKS bootstrapping. And because of this hybrid approach, the reads from the main memory for the bootstrapping keys gets reduced by 18 times. And HEAP outperforms most existing CPU, GPU, FPGA, and ASIC implementations by performing a bootstrapping in just 1.5 millisecond using a fairly small parameter set. Thank you. Happy to take any questions.
Any questions for our speaker? So just to get started. So can you explain a little bit like how do you do the partitioning between multiple FPGAs? Like is it you distribute limbs, or like how do you deal with ciphertext size?
So when it comes to partitioning between different FPGAs, or multiple FPGAs, we typically, so it's like we have already divided the ciphertext into multiple LWE ciphertext. So because there are 8 FPGAs, we can distribute with n equal to 2 to the power 16 parameter set. We can actually have 512 LWE ciphertext on each FPGAs.